The question, which in this case also came from one of our loyal followers, might seem entirely obvious. How indeed could two planets follow the same orbit around a star without eventually colliding? The intuition is sound, and in most cases it is correct. But celestial mechanics is a discipline with a long tradition of making assumptions without verification, and it's best not to trust the obvious too much before looking at the equations. So, if you're curious to know more, stay with us. To understand what really happens when two bodies share the same orbit, we need to take a step back and meet one of the most elegant results in 18th century celestial mechanics, the work of Joseph Louis Lagrange. Lagrange was an Italian mathematician, later naturalized French, who in 1772 published a treatise on the stability of the three-body problem. The three-body problem is notoriously unsolvable in its general form. Given three objects attracting each other gravitationally, there is no exact analytical solution that works for every possible case. But Lagrange found some particular solutions, special cases in which the system behaves in a regular, predictable way. The most famous of these solutions involves a specific situation: a massive star, a planet orbiting it, and a third body much smaller than the other two. Lagrange showed that there are 5 points in space, now called Lagrange points and labeled L1 through L5, where the third body can sit in equilibrium relative to the other two, meaning it can stay fixed in the rotating reference frame that follows the planet in its orbit. The first 3 points, L1, L2, and L3, are easy to picture. L1 sits between the star and the planet, L2 sits on the far side of the planet from the star, and L3 sits on the opposite side of the star from the planet, directly across the orbit. All three lie along the line connecting star and planet, and they share an important feature: they are unstable. An object placed exactly at one of these points will stay there, but the slightest nudge will cause it to drift away, and that drift grows over time rather than correcting itself. Think of them as the top of a hill, perfect balance but precarious. L4 and L5 are different. They sit on the planet's own orbit, 60 degrees ahead and 60 degrees behind the planet's position. Together with the star and the planet, they form two perfect equilateral triangles. And surprisingly, they are stable. An object disturbed from L4 or L5 doesn't drift away progressively. It oscillates around the equilibrium point, like a marble rolling around the bottom of a bowl. Lagrange himself was struck by this result. The stability doesn't come from static geometry, but from the delicate balance between the star's gravity, the planet's gravity, and the centrifugal force in the rotating system. The math only works out if the most massive body, the star, is at least 25 times more massive than the planet, but that condition is almost always met in real planetary systems. For over a century, L4 and L5 remained in a mathematical curiosity with no observational counterpart. Then in 1906, German astronomer Max Wolf discovered an asteroid that didn't follow a normal orbit. It was circling the Sun at the same distance as Jupiter, roughly 60 degrees ahead of the gas giant. They named it Achilles and immediately recognized it as sitting at the L4 point of the Sun-Jupiter system. A few months later, the first L5 resident was found, Patroclus. The connection to the mythology of the Trojan War was irresistible, and these objects have been called Trojans ever since. Today we know of more than 10,000 Trojan asteroids associated with Jupiter, split roughly evenly between the two Lagrange points. They've lived there for billions of years, probably captured during the chaotic early days of the solar system. Mars has its own Trojans. Neptune has several, and so do Uranus and Earth. In 2010, the WISE telescope confirmed the first known Earth Trojan, an asteroid called 2010 TK7, roughly 1,000 feet across, leading our planet at L4 and orbiting the Sun at exactly our distance. It's not a planet, of course, but it shares our orbit, and it has been doing so since before humans existed, without Earth ever encountering it and without ever coming close. That answers the question for the simplest case. A small body can share a planet's orbit by settling into L4 or L5. But the original question was much more ambitious. Can two planets, two objects of true planetary mass, share the same orbit? Here the answer depends on what we mean by planetary mass and on how we evaluate stability over long timescales. The Lagrange points are stable for the third party only if that body is much less massive than the other two. As the mass of the third body increases, its own gravitational perturbations begin to distort the other orbits, and the system can become unstable. Numerical simulations show that two bodies of similar mass sitting at L4 or L5 in a stellar system can coexist stably only if their combined mass remains a small fraction of the star's mass. In practice, two Earth-sized planets could theoretically share a Lagrange point in a system like ours, but stability over billions of years is far from guaranteed and depends sensitively on the exact masses involved and on the gravitational influences of the other planets in the system. But there's a second kind of co-orbital motion that is, if anything, even more surprising than the Lagrange points: horseshoe orbits. To understand horseshoe orbits, you have to abandon the static image of Lagrange points and think dynamically. Imagine two bodies traveling the same orbit around a star, but at different angular positions, one ahead, one behind. Both follow Kepler's law. At the same distance from the star, orbital speed is the same. But if for some reason one of them is sitting slightly closer to the star than the other, Kepler's law requires it to move slightly faster. Over time, the inner body gains ground and closes in on the outer one. When the two bodies get close enough, their mutual gravitational attraction starts to matter. And here something counterintuitive happens. The trailing body, as it approaches, gets pulled forward and slightly inward by the leading body, losing orbital energy. The leading body gets pulled backward and slightly outward, gaining energy. The result is that the roles reverse. The one that was inner becomes outer, slows down, and the formerly outer body is now the inner, faster one. The two bodies swap places and start moving apart, until the whole cycle repeats in reverse. In the rotating reference frame that follows the system's center of mass, the two trajectories trace a shape that loosely resembles a horseshoe, hence the name. This is not a hypothetical scenario. It exists in our solar system and is one of the most spectacular examples of complex orbital dynamics we know of: the Saturn moons Janus and Epimetheus. Janus and Epimetheus both orbit Saturn at about 94,000 miles out, so close to each other that the difference between their orbits is just 30 miles, less than the diameter of Epimetheus itself. Throughout the 1970s, astronomers thought they were looking at a single moon and were thoroughly confused when the position measurements didn't add up. Sometimes the moon seemed to be ahead of where it was expected, sometimes behind. The solution arrived with Voyager 1's images in 1980. There were two moons, and they were periodically swapping orbits. Every 4 years or so, Janus and Epimetheus approach to within a few dozen miles of each other, gravitationally bounce off one another, and exchange orbits. The one that was inner becomes outer, and vice versa. They never actually meet. They never collide. They keep dancing around Saturn in perfect dynamical harmony, like two skaters on adjacent lanes who swap lanes every lap instead of crashing. Janus is about 4 times more massive than Epimetheus, but not enormously larger. This is a real-world case of two bodies of comparable size sharing the same orbit around a planet. The mechanism doesn't depend on Lagrange points at all. It relies on a balance between mutual gravitational pull and the orbital velocity gradient. The system almost certainly has chaotic origins. Both moons are probably fragments of a larger body destroyed in a collision. But once it's settled into this equilibrium, it has proven surprisingly robust. The natural follow-up question is, does this scale? Does the horseshoe mechanism work for real planets, not just Saturn's moons? Numerical simulations say yes, in principle. Two planets of similar mass in a system where the star is massive enough to keep orbits stable could theoretically end up in a horseshoe configuration. The gravitational perturbations from other planets in the system, however, make this equilibrium much more fragile over geological timescales. A crowded solar system like ours, with Jupiter throwing its gravitational weight around, would probably destabilize any planetary co-orbit within a few million years. A system with a single star and just a few low-mass planets might be more hospitable. There's also a third category of co-orbital motion, less well-known than the other two but equally fascinating: quasi-satellites. A quasi-satellite is a known object that is seen from Earth or from any reference planet, appears to be orbiting the planet itself, but technically isn't. It's orbiting the Sun on a trajectory very similar to the planets, maintaining relative closeness for longer or shorter periods before eventually drifting away. Think of it as a fellow traveler on the same highway, keeping pace for years or decades before taking a different exit. Earth's best-known quasi-satellite is called Kamoʻoalewa, an asteroid a few dozen meters across discovered in 2016, which has been accompanying our planet for centuries and will probably continue to do so for centuries more. Kamoʻoalewa follows its relative trajectory so faithfully that Chinese researchers selected it as the target for the Tianwen-2 mission, scheduled for the coming years. It will be the first mission to return samples from an Earth quasi-satellite. Putting these three categories together, Lagrange configurations, horseshoe orbits, quasi-satellites, a much richer picture emerges than intuition suggested at the start. The answer to the question isn't simply yes or no. There are at least three distinct physical mechanisms by which two bodies can share the same orbit without ever meeting, each with its own stability conditions and its own real-world examples. The more ambitious question remains open. In the vast catalog of known exoplanets, do co-orbital systems exist? The current answer is not yet found with certainty, but not ruled out either. The transit method, the main technique by which the Kepler telescope and now TESS identify exoplanets, measuring the dip in starlight when a planet passes in front of its star, could theoretically reveal two co-orbital planets through a characteristic signal, two closely spaced transits separated by the angle the two bodies maintain on their shared orbit. Several research teams have combined through Kepler data looking for this signature, and some candidates have been proposed, but none have been confirmed with sufficient certainty. ESA's PLATO telescope, whose mission is planned for the end of this decade, will bring significantly greater photometric precision and will monitor far more stars over longer periods. If co-orbital planetary systems exist with any reasonable frequency, it's realistic to expect PLATO to find them. The fact that we haven't seen one yet doesn't tell us much. Stable co-orbital systems require specific conditions, appropriate masses and geometries, the absence of massive gravitational disruptors, orbits that have settled into regular configurations, and they may simply be rare. But in a galaxy with 400 billion stars, even rare can mean millions of cases. And there's something almost philosophical in imagining that. As you read this, somewhere in a distant system, two planets are traveling the same path around their star, swapping orbits every few years like Janus and Epimetheus around Saturn, or holding their 60-degree separation the way Jupiter's Trojans have held theirs for hundreds of millions of years. Gravity, given enough time and space, finds equilibria that no one would have thought to look for. Two planets sharing one orbit is strange enough, but what happens when you stack the concepts even further? A binary moon orbiting a binary planet orbiting a binary star. Three levels of paired objects, nested inside each other. Watch, can a binary moon orbit a binary planet orbiting a binary star to see how deep the rabbit hole goes.